Hello, in this video we're going to go over problem number 2 from International Math Competition in 1995. So here is the problem. Suppose f from 0, 1 to r is a continuous function for which the integral from x to 1 of f of t dt is at least 1 minus x squared over 2 for all x between 0 and 1. We want to prove that the integral from 0 to 1 of f of t squared dt is at least 1/3. Okay, so the first thing that I did when I looked at this problem, and again, as usual, not everything I'm talking about here is not necessarily going to be used in a solution, but these are my thought process. So looking at the right hand side, if I look at 1 minus x squared over 2, this is clearly the integral from x to 1 of t dt. And the left hand side is the integral of f of t. So maybe somehow this is kind of related. If I look at these two sides, one of them is integral of f squared, the other side is integral of t squared. So if you take the integral of t squared from 0 to 1, you get t cubed over 3 from 0 to 1, which is exactly 1/3. So I thought maybe somehow I can relate integrals of t and f squared. So that brought me to an inequality called the Cauchy-Schwarz inequality. So let me talk about the Cauchy-Schwarz inequality. So assume you have an inner product. So V is a vector space. And we have an inner product. So this is an inner product on V, which means it is a function satisfying certain properties. It is it satisfies conjugate symmetry, positivity, and linearity with respect to the first vector. Now, if we have that assumption, then absolute value of the inner product between every two vectors is less than or equal to norm of V times norm of W. Now, if you don't recognize all of these, don't worry about it. I'll explain exactly what is being done. For example, and this is the example that I actually need. If you look at all the continuous functions from 0, 1 to r, and if you take two functions in this space, so two continuous functions from 0, 1 to r, then the inner product of f and g is defined by the integral from 0 to 1 of f times g dt. Let's say f of t, g of t. Now, Cauchy-Schwarz inequality tells me integral from 0 to 1 of fg in absolute value is less than or equal to, this is the inner product of the f and g, less than or equal to norm of f, which is going to be norm of f is defined as the square root of the inner product of f and itself, which is square root of integral from 0 to 1 of f squared times norm of g, which is integral from 0 to 1 of g squared. Now, if I write down this inequality for the two functions t and f of t, I would get this. Integral from 0 to 1 of t f of t dt in absolute value is less than or equal to square root of integral from 0 to 1 of f of t squared dt times integral from 0 to 1 of t squared dt. Integral from 0 to 1 of t squared dt is exactly t cubed over 3 from 0 to 1, which is 1/3. We are going to square both sides to see what we get. We get integral from 0 to 1 of t f of t dt squared is less than or equal to 1/3 times the integral from 0 to 1 of f of t squared dt. Okay, so this side is exactly what we wanted to evaluate. What we wanted to show is greater than or equal to 1/3. This side, not quite what we want. Now, if you look at the integral from 0 to 1 of t f of t dt, the question is there any way I can relate this to the given inequality, to the given integral, which was the integral from x to 1 of f of x dx. Now, if you have done some multivariable calculus, you know that there are some ways of relating these by using double integrals. So let's look at the relation between t and x. So let's draw a tx diagram, and let's evaluate the integral from 0 to 1 of, and this would have to be t dt integral from x to 1 f of t dt and then dx. So if you look at this one, you have this region defined by that is given by t goes from x to 1. So t goes from here to 1, if this is 1, and x goes from 0 to 1. So this region, integral over this region, if we call this region R, the double integral over R of f of x dA is the same as integral from 0 to 1, integral from x to 1 of f of t dt dx. This is if you think about this one as a horizontally simple region. Now if you look at this one as a vertically simple region, which we can do by the Fubini's theorem, we can write this one down as the integral from 0 to 1, so dt, t goes from 0 to 1, and then x goes from the bottom, which is 0, and the top, which is t. So this is 0 to t f of t dx this time. Now if we evaluate this one, we're going to get the integral from 0 to 1. F of t is a constant, so we get f of t times x, x equals 0 to x equals t dt. And if we plug that in, we get tf of t dt, which is really related to what we have done before. Okay, so now how do we actually solve the problem? So let's start with the inequality that we were given. We were given that this integral is greater than or equal to 1 minus x squared over 2 for every x. We are going to integrate both sides, so we get 0 to 1, x to 1, f of t dt dx is greater than or equal to integral from 0 to 1, 1 minus x squared over 2 dx. Now we showed that the left hand side is exactly integral from 0 to 1 of t dt f of t dt. If we integrate the original integral, we get this, and this is something we got. That's greater than or equal to, let's integrate that one. Integrating that one, we get x over 2 minus x cubed over 6 from 0 to 1. If we plug in 1, we get 1/2 minus 1 over 6, and then if we plug in 0, we get 0. So that is 1/3. So this inequality is what we obtained. Now looking back and comparing it with what we got before, and by which I mean this inequality, we can actually obtain the result. So how do we do that? We have that integral from 0 to 1 of t dt t squared dt times integral from 0 to 1 of f of t squared dt by Cauchy-Schwarz is greater than or equal to integral from 0 to 1 of tf of t dt. All of that squared. This is Cauchy-Schwarz. And this is 1/9. This one is 1/3. So if we divide both sides by 1/3, we're going to get integral from 0 to 1 of f of t squared dt is greater than or equal to 1/3. So to summarize, what we used was Cauchy-Schwarz inequality, the fact that we can integrate both sides. So the first one was the Cauchy-Schwarz inequality. The second one was if f is greater than or equal to g, then we can get that integral of f is greater than or equal to integral of g if a is less than b, integrating from a to b. And the third thing that we used was the Fubini's theorem, that we can swap the order of integration using double integrals. And putting these three together, we can get the inequality that we were looking for. And that brings me to the end of this video. So if you like this video, feel free to check out the rest of the videos on my channel, and I will see you in the next video.